In this lesson, we're going to learn about the second derivative. When we differentiate once, the expression we get is known as the first derivative. If we differentiate a second time, the result is known as the second derivative. So, if we have an original function y equals x to the 4, if we differentiate once and find dy by dx, we get 4x cubed. That's called the first derivative. If we differentiate again, we get 12x squared. This is called the second derivative, and we write it using d2y by dx squared. If we were using function notation, we know that the first derivative is denoted with f dash x, so for the second derivative we use the notation f dash dash x. So what we're essentially doing when we find the second derivative is finding the gradient of the gradient function. So we say that the second derivative measures the rate of change of the gradient function. If we have a look here at a graphical example, we've got the red curve, which we can see as a cubic, which is our original function, f of x. If we differentiated that, if we differentiate a cubic, because we're reducing the power by 1, we get our function for our first derivative, f dash x, which ends up being a quadratic. And that's our kind of yellowish coloured curve here. If we differentiate again, so if we differentiate the quadratic to get the second derivative, f dash dash x, we're going to get the straight line that's in green here. Because if we differentiate a quadratic, if we reduce the power of squared by 1, we end up with no powers, therefore we have a linear function. Okay, so let's have a look at an example. If we've got an original function here and we're asked to work out d2y by dx squared, we just simply differentiate once. To get our, what's called our first derivative. And then we differentiate again, d2y by dx squared equals 12x minus 8, and that's our second derivative, and that's all there is to it. Let's have a look at an example that represents something in real life. So we've got a ball that's thrown up with an initial velocity of 20 meters per second. We're told that its height h above the ground after a time t is given by this quadratic function 1 plus 20t minus 5t squared. First of all, we're asked to work out dh by dt. So dh by dt, let's differentiate once. We get 20 minus 10t. Then we're asked to say what this represents. So what we've done here is we've differentiated the height, which is a distance. So we've found the gradient function of the distance. Now, if you think back to your kinematic graphs, on a distance time graph, the gradient is velocity. So dh by dt, which is finding the rate of change of the distance, or the gradient of the distance with respect to the time, that must represent the velocity of the stone. Part 2 asks us to differentiate a second time to get d2h by dt squared. So that's just going to give us minus 10. And again, we're asked to say what this minus 10 represents. So what we've done here is we've found the gradient of the velocity. And if we remember, the gradient of a velocity time graph is acceleration. So the minus 10 must represent the acceleration of the stone in meters per second squared. So if we kind of go back to our distance time graph, so our distance time, if we had a distance time graph, so this could be our h and our t. The gradient of that is the velocity time graph. So for the gradient of the distance time graph, we're finding dh by dt, so that gives us the velocity. Once we've got our velocity against time graph, the gradient of that, which is d2h by dt squared, gives us the acceleration. So now I'd like you to have a go at exercise 8E from the Further Maths textbook, the following questions.